So what we'll do is that we had looked into the Fick's first law, if you remember. Uh, I'll just write down the Fick's first law for you. Uh, Here it is. Fick's first law basically relates the flux to the diffusion coefficient and the concentration gradient. This is the Fick's first law that we're looking into. Do you remember this?
Yes, sir.
याद है नहीं याद है सो रहे हो
Sir, याद है sir.
याद है all right now so we'll try to look at an example that addresses or that involves the calculation based on Fick's first law example क्या है कि it first gives a statement that methylene chloride it's a chemical which is an ingredient in paint removers में ingredient use किया जाता है besides being an irritant, although it's an irritant, it may also be absorbed through the skin. So, when using a paint remover, protective gloves should be used. And it further says that if the butyl rubber gloves, the stretchable gloves that you use, if these gloves are used having a thickness of 0.04 centimeter, what would be the diffusive flux of methylene chloride through the glove? So you have to find out the diffusive flux through the gloves for methylene chloride through the butyl rubber if this is the information that is given to you that the diffusion coefficient of this irritant chemical through the gloves rubber gloves is 110 into 10 to the power minus 8 centimeter square per second and the concentrations are given to you. The two concentrations are also given to you, C1 and C2. With this information given to you, can you find out the diffusive flux J? G. Can you find it out?
Yes. Yes, sir.
Alright. So have about 5 minutes and try to solve this and then we'll look at the solution. Alright?
Yes, sir.
Alright. Let me know if you find it out before that. Qasim, are you solving this? Adil, Afraz, Khalid.
जी सर मैं कर रहा हूँ
Alright.
सर मेरा इसका आंसर आया 1.155 into 10 to the power minus 5. सर सेंटीमीटर्स में ही रख के मैंने किया.
All right. So you have got
Sir,
the
मेरा
answer. Just a minute. Yeah, just
1.2 10 raised to minus 5.
1.15
into 10 to the power minus 5.
15 centimeter square. Sorry, it would be grams
Per centimeter square.
centimeter square per second. And the second answer was what? 1.2?
Yes, sir. 1.2 10 raised to minus 5 gram per centimeter cube. Centimeter square. Okay.
All right. Chale, let's have a look at the solution. Solution says that you have to assume a linear concentration gradient. That means Tc over dx is constant. It's not changing. For that, what you have to do is that you assume that on one side you have paint remover where your concentration is high, and at a distance of the glove thickness where you have the contact with the skin, you have a low concentration, and this concentration is varying linearly. With this, you have the relationship J, which is the flux, is negative of the diffusive flux multiplied by the concentration gradient. Excuse me. So, and the concentration gradient is C2 minus C1 over X2 minus X1. Now you know that C1 just represents to higher concentration, C2 represents to lower concentration, X2 minus X1 is essentially the thickness of the glove. Once you plug in the values, you essentially get 1.16 into 10 to the power minus 5 grams per centimeter cube. You could also round it off. It's correct. So both of you have got correct answers. All right. Now, moving on to the understanding of the diffusion coefficient and the effect of diffusion coefficient with regards to temperature. All right. So it says the magnitude of D is indicative of the rate at which atoms diffuse, and it is dependent upon the diffusing species, the element or the material that is diffusing from high concentration to low concentration, and the host material in which the diffusion is taking place. Both influence D. So let's say I have two diffusion coefficients at 500 degrees centigrade. One is 3 into 10 to the power minus 21 meters square per second, and the other is 1.4 into 10 to the power minus 12 meters square per second. And I have two scenarios. One is where carbon is undergoing self diffusion, and the other is where carbon is undergoing interdiffusion in alpha iron. Which of the two coefficients, diffusion coefficients, would represent which mechanism? Could you identify which coefficient would represent which mechanism? Any ideas?
Sir, question repeat कीजिए.
I have mentioned there are two diffusion coefficients. One is 3 into 10 to the power minus 21 meters square per second. The other is 1.4 into 10 to the power minus 12 meters square per second. These two coefficients are at 500 degrees. And I have represented two mechanisms. One is where carbon is undergoing self-diffusion, this phenomena, and the other where carbon is interdiffusing into alpha iron or iron. Which of the two coefficients would represent which mechanism? एक process है जिसमें carbon is diffusing into itself, and the other is where carbon is diffusing into iron. Carbon iron में diffuse हो रहा है. which coefficient or which diffusion coefficient would represent which process? दो जो वैल्यूज हैं इसमें से कौन सी वैल्यू कार्बन की सेल्फ डिफ्यूजन के लिए होगी और कौन सी कार्बन की आयरन? जी सॉरी
कार्बन सर,
सॉरी
कार्बन के लिए 3 × 10⁻21 होगी,
अच्छा
और दूसरी सर उसके लिए मतलब वो आयरन में जो कन्वर्ट होगा उसके।
व्हाई इज इट सो?
सर आई थिंक उसे कम सर लगेगी, कोफिशिएंट उसका कम होगा खुद में जब वो कन्वर्ट होगा।
किसमें कोएफिशिएंट कम होना चाहिए?
सर ये फर्स्ट केस में कम होना चाहिए।
कोई रीजन है जेन में या बस इट्स अ गेस?
सर गैस ही किया सर।
द रीजन बीइंग जब कार्बन कार्बन में डिफ्यूज हो रहा है तो इट्स अ वेकेंसी डिफ्यूजन प्रोसेस, और जब कार्बन आयरन में डिफ्यूज हो रहा है तो इट्स एन इंटरस्टिशियल डिफ्यूजन प्रोसेस, और इंटरस्टिशियल डिफ्यूजन जो है इट इज फास्टर, दैट्स व्हाई यू हैव अ डिफ्यूजन कोएफिशिएंट व्हिच इज फास्टर फॉर carbon in iron and as compared to carbon in itself. All right, जितना डिफ्यूजन कोएफिशिएंट बड़ा होगा उतना डिफ्यूजन जो है वो आसान होगी या तेज होगी। Anyways, moving on to the effect of temperature. Temperature has a profound influence on the diffusion coefficient. For example, self-diffusion of iron in iron diffusing in itself, the diffusion coefficient increases from 3 into 10 is to the power minus 21 to 1 into 1.8 into 10 to the power minus 15 as the temperature was increased from 500 to 900 degrees centigrade. All right. Uh, this increase is basically due to the creation of vacancies. Now, the relationship of diffusion coefficient D with regards to any temperature is related by the Arrhenius equation, where D is the diffusion coefficient in meters square per second at a specific temperature T, and T is the absolute temperature. QD is the activation energy, R is the universal gas constant 8.314 joules per mole per Kelvin, and D naught is a constant which is a pre-exponential constant. You have seen a similar equation for the number of vacancies, equilibrium number of vacancies. Now, this equation is for the diffusion.
का नाम क्या सर
जी
इस
sorry.
इक्वेशन का? सर इस इक्वेशन का नाम क्या सर?
These equations where you have exponentially increasing terms, normally they are known as Arrhenius equations. All right. It's a generic form of the equation. Arrhenius is a generic form of the equation. These equations were, you have seen a similar equation for the number of vacancies, if you remember. Anyways, we'll try to solve an example for this equation, and would see how this equation affects or is being applied. So it says at 300 degrees centigrade, the diffusion coefficient and activation energy for copper and silicon are. So at 300 degrees centigrade, the diffusion coefficient D is 7.8 into 10 power 11 minus 11 meters square per second, and QD activation energy is 41.5 kilojoules per mole. Now, what is the diffusion coefficient at 350 degrees centigrade? This is what you have to find out. If I write down the equation for you, D is essentially equal to D naught exponent of minus Q D over R T. D naught would remain the same whatever the temperature. QD would remain the same, R would remain the same. So you have two variables T and D. For one condition D1 and T1 are given. For the second condition you have to find D2 for the temperature T2 which is given to you. Alright. The value of QD is given, R is 8.314 joules per mole per Kelvin. So you have to find out the diffusion coefficient at 350 degrees centigrade. Can you find it out?
Yes, sir.
All right. So have about 5 minutes, try to solve it, and if you have found it out, let me know.
Sir, 15.7 into 10 raised to the power minus 11.
G, one answer that
15,
I've got is uh,
15.7
just a minute, 15.7
into 10 raised to the power minus 11.
meter square per second. अच्छा चले right, this is one answer. Anybody else who is in the process of solving?
Yes, sir.
All right, find it out and let me know the value.
Sir, 15.6 into 10 to the power minus 11 meters square per second.
All right, I've got another answer. Sorry, says 15.6 into 10 to the power minus 11.
Meter square per second.
It's almost a similar answer. Anybody who has got a different answer? No? All right. Before I move on towards the solution, let us first look at the curves for the two variables. The diffusion coefficient is related to the temperature in an exponential manner. That as the temperature is increasing, the diffusion coefficient increases exponentially. It's easier for us to transform the data in the natural log form. For example, if I have this equation over here, d equals to d naught exponent minus qd over rt. If I take the natural log on both the sides, what I'll get is an equation which is something like this. ln d equals to ln d naught minus qd over rt. Correct? Is it understood?
Yes, sir.
All right. Now, ln d is a variable which we can replace with y. Natural log of d naught is a constant, so natural log of d naught would also be a constant. Let's represent it with c. Minus q over minus qd over r. Let's represent minus qd over r with a constant, let's say, which is m. And 1 over t, let's represent 1 over t, this 1 over t with another variable which is x. So it's a equation of straight line where x is 1 over t and y is natural log of d. So if you draw an equation between natural log of d and 1 over t, you will get a straight line in which the gradient is qd over r. It's a negative sign, and the equation would cut the x's at point somewhere at c. It's a constant. All right. Now with this equation, what we can do essentially is we can write two equations. We had 2 points given to us for point 1 d1 and d1. They are given to you 300 degrees centigrade and 7.8 into 10 to the power minus 11 meters square per second. That is the d1 value. For the second state, you have been given with the temperature which is 350 degrees centigrade, and D2 is to be calculated. If I subtract this equation and I have this equation, if I subtract equation 1 from equation 2, subtracting 1 from 2, what would essentially happen would be I'll have natural log of d2 minus natural log of d1. The constants ln d naught and ln d naught would cancel out. And when I subtract these two terms, I'll have a negative sign of minus qd over r. This is the common factor. This would come outside. And 1 over t2 minus 1 over t1 would be inside. With this equation over here, so I had the equation ln d2 minus ln d1. This is equals to minus qd over r 1 over t2 minus 1 over t1. So I can write this expression as ln d2 whole over d1 equals to minus qd over r 1 over t2 minus 1 over t1, and then I can take the natural log on both sides. So this term exponent would come with this expression, and then I can move d1 from over here to the right hand side. In this equation, if we see, temperatures have to be taken in absolute scale. So T1 is given to us, T2 is given to us, the coefficients, the diffusion coefficient D1 is given to us, which is being plugged into over here, and D2 is calculated. Remember that the QD value was given in kilojoules per mole, 41.5 kilojoules per mole, so you had to convert it into joules per mole, and this is your value of diffusion coefficient, 15.7 into 10 to the power minus 11 meters square per second. So your answers 15.7 or 15.6 were correct. All right. Now, moving on towards another concept, which is the dependence of diffusion coefficient with temperature. You already see uh, the log of d or ln d versus 1 over t plots. You've already seen them. Now, if we plot the natural log of d versus 1 over t plots for different combinations of or different pairs of diffusion species, you would see aluminum in aluminum, iron in iron, and iron in gamma iron. It's essentially two phases, but it's a vacancy diffusion process. And then you have carbon in alpha iron and carbon in gamma iron. If you look at this axis over here, the temperature is increasing in this direction. This is the direction in which temperature is increasing. The first thing you should note is that the diffusion coefficient of these three are less than for these two pairs. If you compare the diffusion coefficients for the bottom three pairs, they are less than the top pairs. Why is it so?
सर वो वैकेंसी और इंटरस्टिशियल.
Very good. So these three mechanisms are for vacancy diffusion, and these three are interstitial. These two are interstitial, the top one. And the effect that you see of the temperature का effect क्या नजर आ रहा है? How is temperature affecting?
सर टेम्परेचर डिक्रीज हो रहा है सर.
और अगर टेम्परेचर डिक्रीज हो रहा है तो डिफ्यूजन कोफिशिएंट पे क्या इफेक्ट आ रहा है?
सर वो डिफ्यूजन कोएफिशिएंट सर वो इंक्रीज हो रहा है.
डिफ्यूजन कोफिशिएंट इंक्रीज हो रहा है, टेम्परेचर डिक्रीज हो रहा है तो.
यस.
लुक एट इट वेरी केयरफुली.
सर ये उल्टा बता रहे हैं
सर वो हाँ सर वो मैं वो
सर.
नेगेटिव.
टेम्परेचर इंक्रीज हो रहा है और डिफ्यूजन कांस्टेंट डिक्रीज हो रहा है.
टेम्परेचर इंक्रीज हो रहा है और डिफ्यूजन कोफिशिएंट डिक्रीज हो रहा है.
सर टेम्परेचर डिक्रीज ही हो रहा है और वो भी डिक्रीज हो रहा है सर डिफ्यूजन कोएफिशिएंट
जी
सर।
बिल्कुल। और इन अदर वर्ड्स, अगर मैं यहाँ से यहाँ मूव करूँ तो, एंड इफ आई लुक एट, ऑलराइट बिफोर दैट लेट मी इरेज, अगर मैं इस डायरेक्शन में मूव कर रहा हूँ तो मेरा डिफ्यूजन कोफिशिएंट, let's say if I'm moving in this direction, the temperature is increasing and so is my diffusion coefficient. Is it the case?
यस सर।
All right. So you've already seen that the interstitial diffusion coefficients, they are much faster or much higher value as compared for the substitutional diffusion. Now, so far you have seen the case of steady state diffusion. We'll now be looking into the concept of non-steady state diffusion process. It says mostly diffusion occurs in non-steady state condition. आपने जो पहले alright, before that, so what is happening is that the flux of diffusing species or concentration gradient at a particular space is varying with time. पहले ऐसा केस नहीं था जो आपने फिक्स फर्स्ट लॉ देखा था. You said that there was a diffusion taking place from C1 concentration to C2 for this distance x, but whether the time was 0 or time was 2 hours, this the concentration gradient remained the same. At a particular point, the concentration was not changing with time. If you look at this curve, concentration of diffusing species against distance for different times. So let's say I have a rod over here. If I look at different distances, let's say at distance x1 and let's say at distance x2, within the rod the concentration is changing. Sorry. With regards to distance, the concentration is changing. But with regards to time, the concentration is also changing. For this distance x1, at time t equals to t1, this is the concentration C1. At time t2, this is the concentration C2. And at time t3, this is the concentration C3. So with regards to time, the concentration at a particular time is also varying. This is a non-steady state diffusion problem. Is this point clear?
यस सर।
All right. So in order to solve such a problem, you will have to develop another law. Fixed first law cannot be used. Height cannot be used because there would be net accumulation of species at a given place. If I look between these two regions, with the passage of time at this location, the number of species or the concentration is increasing. And if I look at this point, the number of species are also increasing. So there would be accumulation of species at a given place. The concentration would increase with regards to time. This was not the case when you were looking at the fixed first law because you had a constant gradient and at any time t equals to any value you had the same concentration. That's the difference. So now let's start to look into how can we develop a relationship for the fixed second law. It says flux J at any point along x-axis will depend upon the local value of the diffusion coefficient, and the concentration gradient. Now, if you remember, this is the equation for flux, which says the flux is dependent upon diffusion coefficient and the concentration gradient. And if we have a concentration profile along one direction, next direction, which is changing in this way. So if you have this concentration profile, and if you look at the gradients, the gradient at this point and the gradient at this point, are they same or different?
सर डिफरेंट है.
तो आपने दो पॉइंट लिए, x लिया and a point which is slightly farther away from x, and you see that dc over dx at this point is greater than dc over dx plus delta x. Clear? इस पॉइंट पे जो ग्रेडियंट है वो कम है और इस पॉइंट पे जो ग्रेडियंट है वो ज्यादा है. इज दिस क्लियर?
यस सर.
इसका इफेक्ट क्या होगा कि you will have the flux at point 1, the flux is higher as compared to the flux at point 2 because it is dependent upon the gradient. Diffusion coefficient तो same है material का और pair का, so J1 would be greater than J2. Clear? Yes, no?
यस सर क्लियर है सर. वो मैं नोट करने लग गया था, कोई और बोल ही नहीं.
All right. Now, if you look at this small portion of the material, ये मटेरियल का क्रॉस सेक्शनल एरिया है, ठीक है, ये क्रॉस सेक्शनल एरिया है और ये डेल्टा एक्स डिस्टेंस है. अब अगर J1 is greater than J2, तो जो एंटर हो रहा है वो ज़्यादा है और जो लीव कर रहा है मटेरियल एरिया से वो कम है, तो इसका इफेक्ट क्या होगा? If the species entering is more, flux J1 is more as compared to G2, तो इफेक्ट क्या होगा?
सर एक की मतलब
जी,
कंसंट्रेशन बिल्कुल ज्यादा हो जाएगी एक की और दूसरे की कम हो जाएगी सर.
इस रीजन में क्या
मटेरियल
इफेक्ट? जो J1
सर वो
है दैट
कांस्टेंट
इज,
के सर वो नॉन स्टेडी हो जाएगा, स्टेडी नहीं रहेगा
वो
सर.
तो ठीक है. अगर फ्लक्स आ ज्यादा रहा है और निकल कम रहा है तो
सर
अल्टीमेटली
इस जगह पे अक्यूमुलेट हो
सर
जाएंगे.
एक्यूमुलेशन शुरू हो जाएगी. वेरी गुड. You will have atoms start getting accumulated within this region. All right? Clear है ये चीज?
यस सर.
अच्छा, अगर और J1 होता क्या है? J1 if you remember is grams और atoms per meter square per second, ऐसे ही होता है ना? फ्लक्स है ना? नंबर ऑफ एटम्स पर मीटर स्क्वायर पर सेकेंड या ग्राम्स पर मीटर स्क्वायर पर सेकेंड. क्लियर? फ्लक्स क्या है? यही चीज है. ऑलराइट. तो अगर इफ आई मल्टीप्लाई J is essentially number of atoms or grams per unit area per unit time. So if I multiply this by area and time, I can find out the number of atoms that are entering a particular area for a particular time. So if I multiply J1 with the cross-sectional area and a small time delta t, I would have the number of atoms that are entering through point 1 into the region. Clear? J1 multiplied by cross-sectional area multiplied by delta T would give me the number of atoms that are entering into the region. Clear hai?
यस सर.
Yes, sir.
Similarly, J2 multiplied by the cross-sectional area multiplied by the same time would give me the number of atoms that are diffusing out of the region. All right. Yes, no.
Yes, sir.
All right. So number of atoms getting accumulated within this region for the time delta t would be J J1 minus J2 into area into delta t. Clear है ये चीज?
Yes, sir.
All right. अच्छा, और concentration को हम कैसे define करते हैं? Do you remember how do we define concentration?
Yes, sir, समझ आ गई.
Concentration is essentially number of atoms per unit volume. So if I say this expression represents number of atoms getting accumulated, A into delta X would be the volume of this region, the volume of the region, and change in concentration of the region is essentially change in number of atoms or number of atoms accumulated divided by the volume of the region. Is this clear?
Yes, sir. Concentration will be number of atoms per volume.
G. And if you look at this expression, you can cancel area with area, and you can take delta T onto this side. So you'll have an expression which says that small change in concentration with regards to small change in time is essentially equivalent to change in flux divided by change in the distance. Why do you have a negative sign? The change in flux delta J is essentially J2 minus J1. Alright? Here you have J1 minus J2, which is a positive value, since J1 is higher than J2. But J2 minus J1 would be a negative value, that's why you have negative sign over here. Alright? Clear enough? Alright. Moving on, for very small value of change in distance and change in time, you can represent these changes in differential form, and you can say dC by dt, the gradient, concentration gradient with regards to time,
सर
essentially,
बहुत ज्यादा आ रही है सर ये
sorry,
सर का माइक ऑन है उसकी वजह से बहुत ज्यादा डिस्टॉर्शन आ रही है सर
could
Ali
you
Hassan
please
Kamai.
turn off your mic? Is it better now?
Yes, sir.
यस सर
Yes, sir.
So ये चीज क्लियर है आपको? यहाँ तक क्लियर है? ये एक्सप्रेशन क्लियर है?
यस सर
Area is essentially cancel out, delta T was brought over here, J1 minus J2, जब हम चेंज की फॉर्म में लिखेंगे डेल्टा J is essentially J2 minus J1, तो वो नेगेटिव साइन बाहर आ जाएगा, and you can represent it with delta J, small change in J. Now when you have very small change in X and T, small changes in distance and small changes in time, you can represent this expression or these expressions in differential form. You can say dC by dt is essentially the gradient of concentration with regards to time is essentially equivalent to negative of the differential of flux with regards to displacement. And what you can do is that you can replace flux with the fixed first law, which says J is essentially equivalent to minus d over dc over dx. These minus would cancel out, and you would have an expression which says dc by dt, the change in concentration with regards to time, is essentially equivalent to diffusion coefficient multiplied by the second derivative of concentration with regards to the displacement. Now, this is a partial differential equation. I hope you are familiar with the partial differential equations. Are you familiar with the partial differential equations? पढ़िए.
सर जिसमें सेकंड और थर्ड डेरिवेटिव लेते हैं.
नहीं, जिसमें basically you have derivatives with regards to two constants, two variables.
सही.
एक equation में temperature और displacement दोनों के साथ derivative ले रहे होते हैं. Anyways, so again for partial differential equation, the problem is that solutions to this partial differential equation for both position and time, concentration in terms of both position and time, they are possible only when you have physical meaning of the boundary conditions. कोई physical boundary conditions available हो आपके पास. So हम एक एग्जांपल एक खास किस्म की प्रॉब्लम के लिए बाउंड्री कंडीशंस डिफाइन करेंगे and we'll try to look at the solution. Alright, so a practically important solution is for a semi-infinite solid. Carburization के example लेंगे. For the example of carburization, we'll look into the solution for this partial differential equation. और उसके लिए जो boundary conditions है, the boundary conditions that we have specified is that this is a semi-infinite bar. ये बार है स्टील की, जिसके अंदर at time t equals to 0 concentration जो है वो C0 है. एक फिक्स्ड कंसंट्रेशन है बार के अंदर ऑफ कार्बन एटम्स एट टाइम t equals to 0 and that concentration is C0. दूसरी बाउंड्री कंडीशन ये है कि एट ऑल द टाइम्स t greater than equal to 0, एट ऑल द टाइम्स जो सरफेस पे एक्सपोज्ड कंसंट्रेशन है that is CS and it remains the same. Alright, concentration CS है और यहाँ it remains the same for whatever time you're talking about. So these are the boundary conditions. The first is that at time t equals to 0, C equals to C0 for 0 to infinity length. पूरी रॉड के अंदर जो कंसंट्रेशन थी वो C0 थी. At time t greater than 0, C equal to CS for x equals to 0, यानी कि यहाँ पे सरफेस जो है उसकी कंसंट्रेशन CS है at x equals to 0 and at a distance which is at infinity length at x equals to infinity और बहुत दूर, इस सरफेस से बहुत दूर, the concentration remains C0. So if you look at a distance over here which is let's say far enough, तो concentration यहाँ पे whatever the time you have is C0 और time t equals to 0 के ऊपर throughout the rod you had the concentration C0. Is this distribution or boundary conditions clear to you?
Yes, sir.
All right. So for these boundary conditions, we'll look at a solution. Solution क्या है कि CXT concentration at a distance x at a time t minus the initial concentration C0 divided by the concentration at the surface minus C0. This would be equivalent to 1 minus ERF is a function. We'll see what this function is. And function value is dependent upon x, the distance, time, and the diffusion coefficient. So if we know the distance, time and diffusion coefficient, we can find out the concentration at a specific distance and time. We can also write this value as z, and error function z is a function which says that if you know the value of z, you can find out the function value at z using this expression, which is 2 over under root pi integral of e to the power minus y square dy from 0 to z. Now you don't need to find out or integrate this expression for yourself. This has already been done for you. You have a table for error function z values which are given in table 5.1, or the table is shown over here. So if you know the z value, in simple words, if you know the value for this expression which is z, you can go to the table. Let's say your z value is 0.25, corresponding error function z value is already been calculated for you, error function z value. So you can directly use this value, error function z value, in the expression and find out the concentration at a specific distance for a specific time. Clear enough? Yes, no?
Yes, sir.
Yes,
All right.
sir.
Yes,
So we'll try to look into this second law expression
Yes, sir.
for the carbonization solution by virtue of an example. It says that an FCC iron carbon alloy initially containing 0.28% of carbon is carburized at an elevated temperature in an atmosphere that gives surface concentration of carbon at 1 weight percent. If after 49.5 hours the concentration of carbon is 0.35 weight percent at a position which is 4 millimeters from the surface, determine the temperature at which the treatment was carried out. Now this problem looks somewhat difficult. So the first thing we do is we write down the information that is given to us. Can you tell me what is the value of C naught?
Sir, 1.0.
C naught होता क्या है? If this is my rod, तो कार्बन की कंसंट्रेशन एट T equals to 0 पूरी रॉड में बराबर होती है, तो वो क्या होती है?
So 0.2 में होगी.
जी, very good. 0.2. It is the initial concentration of carbon within the rod. CS क्या होगी? Surface concentration.
Sir, 1 weight
जी,
percent.
1 weight percent. It is exposed in an atmosphere that gives surface carbon concentration of 1 weight percent. And what would be CXT?
Sir, 0.35.
0.35.
0.35. And this value corresponds to the time equals to 49.5 hours, and the distance is essentially 4 millimeter. So these four values are given to you. Can you find out the value for, can you find out error function z क्या है? This is z. Error function z क्या है, ये find out कर सकते हैं? जी, can you find it out? Yes, no? Can you guys hear me?
नो सर, इसकी नहीं समझ।
जी, आवाज आ रही है आप लोगों को?
यस सर, आ रही आवाज।
आप एरर फंक्शन z, अगर मैं ये कहूं तो ये वैल्यू फाइंड आउट कर सकते हैं? बिल्कुल खामोशी छा जाती है। एटलीस्ट गिव मी एन आंसर, यस, नो।
Yes sir.
Yes, sir. Yes, sir.
So what would be the value of error function z?
Sir, 0.8125.
Error function z is
8125.
0.8125. तो अगर मुझे एरर फंक्शन z पता है, कैन आई फाइंड आउट द वैल्यू ऑफ z?
Yes, sir.
Yes sir, तो टेबल से सर करके सर हम फाइंड कर।
सॉरी,
सर टेबल से देख के सर डाल लें।
ये ले टेबल। कैन यू फाइंड इट आउट?
सर 0.9 से 0.95 के दरमियान आएगी सर।
जी, इफ यू लुक एट दिस एक्सप्रेशन, जो आपकी एरर फंक्शन की वैल्यू आई है 0.8125 समथिंग, इन दोनों वैल्यूज के दरमियान में, so your z values would also be in between. But how to find out the value? So let's first look how would you find out the error function z value. आपने तीनों concentrations plug in कर दी, you subtracted it from one, this expression, and you get the error function z value of 0.8125. Now the problem is when you go to the table, uh, you see that 0.8125 lies between these two values, and there is no exact value given for this error function value. So what you do is that you use the interpolation function. Interpolation क्या है? Basically, if you have a straight line और आपको x1 y1 पता है, similarly आपको x2 y2 पता है, तो आप इसी ग्रेडियंट के ऊपर इफ यू हैव द x3 वैल्यू तो आप y3 फाइंड आउट कर सकते हैं. Essentially what you are doing is that on one side you are taking the ratio for the differences in z values, and on other side you are taking the ratio for the differences in error function z values. Now the important thing over here is, let's say I have written z minus 0.90 over here. I would write the exact values for error function z on the other hand side. यहाँ पे z की वैल्यू और इसके corresponding 0.90 के corresponding error function z की वैल्यू. Similarly, I have taken the difference in these two values for z, 0.95 and 0.90. तो यहाँ पे 0.95 के corresponding value और subtract करूँगा 0.9 के corresponding value. Now when I solve this, I can find out the value for z. ये ऐसे भी कर सकता था कि I would have written ये z के लिए है, ये एरर फंक्शन z के लिए है, बीच में इक्वल टू का साइन आ गया, तो I could have written 0.90 माइनस z, ये भी कर सकता था, और डिफरेंस में ले सकता था ऐसे ही, किस तरह भी लिया हुआ है इन दोनों का 0.95 माइनस 0.90. लेकिन जब यहाँ पे वैल्यूज लिखूँ ऑन द राइट हैंड साइड, तो पहली वैल्यू 0.90 के कॉरस्पॉन्डिंग मेरे पास है 0.7970. आई राइट 0.7970 माइनस z के कॉरस्पॉन्डिंग वैल्यू जो है 0.8125 है, सो आई राइट 0.8125, एंड देन आई विल टेक द वैल्यू फॉर 0.95 व्हिच इज 0.8209, इसके कॉरस्पॉन्डिंग वैल्यू माइनस 0.7970, 0.7970, the value corresponding to this point. इसको solve करके I can find out the value for z. Clear enough?
Yes, sir.
Yes.
All right. So once you solve, you find out that z value is 0.93, or z, if you remember, is this expression, x over 2 under root dt. Or if I want to find out the value of d, it is essentially x square over 4z square t. So I can find out by plugging in the x value again in meters, time in seconds, the z value, to get the diffusion coefficient. Diffusion coefficient तो मुझे मिल गया, but what was my interest? Find out क्या करना था? हमें find out करना था
Temperature.
temperature at
Temperature.
which this process took place. So now you will go back and use this diffusion coefficient to find out the temperature. Again, moving back to the Arrhenius equation. Diffusion coefficient given है D naught QD, you will find out from the table, and using these values you'll find out the temperature. If you go back at the statement and look at the statement, it says FCC iron carbon alloy. FCC iron is basically gamma iron, and carbon is diffusing into gamma iron. Now, if you go to the table, this table would be shared with you. This is a table which says diffusing species. Diffusing species is carbon. Host material. Host material is gamma iron, as it is being said in the statement. Gamma iron is FCC iron. The D naught value is 2.3 into 10 to the power minus 5. The activation energy is 148 kilojoules per mole. With these values, so if D naught is known to you, QD is known to you, R is 8.314, and diffusion coefficient you have already found out in the last slide, which is 2.6 into 10 to the power minus 11 meters square per second. With this information known to you, what you have done is again you have rewritten the expression. If you remember, ln d equals to ln d naught minus qd over rd, or you can write qd over rd equals to ln d naught minus ln d, and if I make t as the subject of the formula, I'll have qd over r multiplied by ln d naught minus ln d. So this is the same expression. QD is given to you. D naught you have found out from the table. R is 8.314. D is you have already calculated. This would give you the temperature. Just plugging in the values. Again, remember, QD value was given in kilojoules, so you have to multiply it by 1000 so that units are consistent. These values were given to you, and this gives you the temperature, which is 1300 Kelvin or 1027 degrees centigrade. Clear enough? इसमें कोई doubt?
No, sir.
Right. So